introduce Martial. And all I know is that he graduated from Princeton, but I think his work precedes him, so I don't need to introduce more. And let's leave all the time to him.
Okay, thank you for the invitation, and thank you for coming to my class. And my class is this is the second lecture on our recent work, which proved the global validity of the Boltzmann equation. And in the lesson, okay, let me first start with a recap of what we have discussed in the lesson. In the lesson, Yu introduced basically three main topics. The first one is the hard-sphere system. The hard-sphere system consists of n particles, and those particles are of radius epsilon. And when those particles do not collide with each other, they just freely transported. And when two of them touch with each other, those two particles will be scattered according to the following scattering rule. Let us denote the vector from the left bar to the right bar by omega, and they will be scattered according to the following scattering rule. That's basically all what you need to know about the hard-sphere system. And for a bar, we will use x to denote the coordinate of its center of mass, and we will use the vector v to denote the direction of its its velocity, and we will use the letter z to denote the whole configuration of the particle. So this is the hard-sphere system. And in order to prove the Boltzmann equation, we need to introduce some probability. And in the lesson, we introduce the concept of canonical ensemble and the grand canonical ensemble. The canonical ensemble is the hard-sphere system where the number of particle n is a fixed value. And in this case, the system is completely determined by the so-called density function. This is just a probabilistic density function. And given a density function Wn, the probability of some events can be computed using the following formula. And here, it's not the actual density function in the probability theory because we have this factor 1 over n factorial. But this function multiplied with the factor 1 over n factorial will be the density function in the probability theory. And we also introduce the notation the vector Zn. Although Z is also a vector, but we do not use a vector notation. The vector Zn always denotes the whole configuration of all the n particles. And dZn means the product of dZ1, dZ2, all the way to dZn. So this is how do we compute the probability. And for canonical ensemble, we can also introduce a notion of a marginal distribution. Marginal density function. This is the function defined by the following, which equals to the marginal density function in the probability theory. Okay, this is a canonical ensemble, the notation for the canonical ensemble. I repeat it because we will use a notation, and the notation is a little bit different from what Yu has discussed in the lesson. For the canonical ensemble, for the grand canonical ensemble, the number of particles will be a random variable. And now we do not just have one density function, we will have a family of density functions. And now the probability should be computed in the following way. PA equals to sum over different number of particles. And Wn corresponds to the density of this probability, which equals to the following. So this is the density function. And the same as the canonical ensemble case, we again need the notion of a marginal density function. In the canonical ensemble case, the marginal distribution is defined by the following formula. And this marginal function is constructed basically using the same heuristic as the construction of this probability. We need to sum over different possibility of the number of particles. And when we fix the number of particles, the expressions is basically the same as the marginal density functions in the canonical ensemble case. But here we have an actual factor. Let me do not explain this actual factor. Yeah, it's not something very important. Okay, that's what we have discussed in the lesson. Before we move on, let me ask if there's any questions. Okay, great. In the lesson, we also introduced the molecule chaos hypothesis, and we use this hypothesis to prove the Boltzmann equation.
Actually, I do have a very fast question. Can you explain the underlying space of your canonical ensemble?
That's something I don't want you to pay attention to. Yes, it will waste some time. Sorry about that. We can discuss this after the class. By space, are you meaning the space of integral? Yeah, this A is. Yeah, I mean this A is union of several different A's. It can have intersections with systems with different particles.
Space and you have a huge measurements.
Yeah.
What is this?
Yeah, let's just keep the most simplest intuition and do not care about so much technical detail. Okay. In the lesson, we introduced the so-called molecule chaos hypothesis, and we use this hypothesis to prove the so-called Boltzmann equation. This hypothesis can be written as the following. Assume that initially the marginal distribution function, or in another word, correlation function, is of the following form. Then, what we need to show that this assumption still holds true at the later time. And it is the standard theorem in the textbook of in any statistical physics textbook. I would denote this hypothesis by Pi. P means propagation of independence. So it's a standard theorem in the textbook of statistical physics. That is the independence of the propagation of independence. The Pi assumption implies the Boltzmann equation. And I think we have proved this in the lesson. And in the lesson, we also introduced the so-called Lanford theorem. The Lanford theorem proves that the Pi assumption is true if the time t is much less than 1. And therefore, combining these two theorems, we have a rigorous justification of the Boltzmann equation if the time t is not very large. Is there any question? This is what we have discussed in the lesson, and in this time, since we have known that the the propagation of independence implies that the Boltzmann equation, and after that, in my class, I will only discuss the PI assumption, and I will discuss the global strategy of how do we prove this PI assumption. Let us first try the simplest method. It's so simple, and so we definitely try it, which is called bootstrap method. Let us assume that let us only take time to be some discretized value, t equals to L tau, and tau is a constant which is much less than 1. Tau is the time where the Lanford theorem holds true. So the Lanford theorem, let us copy down the PI assumption at this discretized value of time. And if you know this assumption by PIL, and the Lanford theorem, implies that if you have PI 0, then you automatically have PI 1. And we may naturally ask the question that can we, in some sense, bootstrap the short result? That is conditional, starting with the assumption of PI 0. That is initially the marginal distribution functions are independent. Lanford theorem tells us that at the later time tau, it's again independent. And now, tau is another time, starting from this time. Can you try to apply the Lanford theorem again? You know, we have independence at this time. Can we repeat the proof again and get independence at the later time? And can we even repeat the process for a lot of times? And finally, can we get the PI capital L for a very large L? If we can really repeat the process, we will prove the PI assumption for a very long time, and therefore we get a global justification of the Boltzmann equation. That's one strategy. However, this strategy doesn't work due to one paradox that we have discussed. That is the paradox of irreversibility. This paradox can be explained as following. Assume that at some time L tau, the marginal distribution function is a product of is a tensor product of some function, and then we can apply. Let's assume that there's no error. Let us assume that the error here is 0. That is, it's perfectly independent. Then, applying the Lanford's proof. Actually, this doesn't really depend on Lanford's proof. For any proof, you can show that you can show the following. some error. What is really problematic is that here we have absolute value of t. We have this absolute value t because the Newton's second law of the hard sphere system is a reversible system. So starting from L tau, going forward and going backwards will give you the same result. So actually you get the absolute value of t. This will cause a big trouble as let's take L equals 1 and assume that we consider the solution at top. If this kind of strategy really works, it tells us that regardless of going forward or going backward, you will get n2 tau at t equals to 0 and t equals to 2 tau. You get the same result. But that is impossible because going backward in the Boltzmann equation must return to the initial value. So this is the problem of the strategy. Is there any questions?
Yes, a comment. In the Lamford paper, it's written explicitly that there is a lack of topology, so it doesn't make sense.
Yeah.
Okay, I'm sorry. Yeah, it's that if you put an error 0, you don't see the main point. Anyway.
Yeah, but even if you take L equals to 0, going forward and going back, at 0 you can also go to the negative.
But the errors are small in different topologies, so you cannot apply the argument.
Yeah,
It was a century ago.
Yeah. I mean, I just want to explain some of our technical problems.
Sorry.
Yeah. Okay. Now, what is the technical reason of this failure? Because it looks like, due to our previous explanation, the Lamford strategy looks like that it works. What is the problem? The problem actually appears in the arrow.
Excuse me. So here, f lt plus t, right? L tau plus t, and solved by particle system, so should be t abstract, absolute value of t, right?
Yeah, I mean, here is the absolute value of t, and here is no absolute value.
No
of
absolute
t.
value of t. So there's a okay. So
This is because starting from L tau, going forward and backward is the same as Newton is just the Newton equation is irreversible. It's reversible system. Okay. So now let me explain the technical reason why Lamford theorem doesn't work. Lamford theorem can only if we write down every detail explicitly, we will realize that the Lamford theorem can only show that given particle independence assumption without any error, it implies the particle independence assumption plus some error. This error is not arbitrarily small. It is only small in L1 space. And here, for Lamford theorem, we may not be so restrictive. We can allow some error in the initial data, but the weakest thing that we can hope is our infinity error.
So I have a small question about the absolute value. I don't understand. I'm not familiar with this. Suppose I have a line of particles all going straight, like Newton dynamics, straightforward. Okay.
Yeah.
And then how is it absolute value? It's not.
No, your particle has a fixed distribution, so you cannot say all your particles are having the same velocity. Like this is a zero measure set.
Yeah, that's a problem. Thank you. Yeah, thank you for answering. Okay. We may not be so restricted. We can count a lot of error, but if you carefully check this error never matches. So the bootstrap doesn't really work. And there's a physical interpretation of this L1 error. So let me, because L1 looks like it's just mathematical, it doesn't really have any, doesn't relate to any physics. But this is true. This is wrong. There's a clear physical interpretation of the L1 error. Actually, we can show that given the independence assumption at the beginning, we can show that L top plus T is almost factorized. Actually, this approximation in some terms is very, very good, and in some terms it's very, very bad for some rare events. This approximation can even of error of 1 or even larger, but for most of the events, the error is but if we take the initial data to be outside of these rare events, this error is O epsilon. And this OL1 just sees that is equivalent to the fact that this O1 error is a rare event. And what does this rare event look like? This rare, for simplicity, let us take L equals 1. These rare events is basically the events that there's two particles collide with each other at the time interval 0 to tau, and so this is the event, and this is basically what the L1 arrow looks like. It is something which it is some function which concentrates near some rare events, and the rare events is some events where there's two particles collide with each other. And now, using this physical picture, we can explain the reversibility and the irreversibility more carefully. In order to show something like a Pi1 plus OL1 epsilon implies that Pi2 plus some OL1 epsilon.
Excuse me, can you explain why this event is a rare event? Because tau is very small? Or?
No, because those two particles have very small radius.
Okay.
So, the fact that two small radius balls collide with each other is a rare event.
Because two given particles.
Two given particles. Not one particle collides with one new particle. Two given particles. Okay. In order to show Pi1 plus the L1 error implies that Pi2 plus L1 error, we need to show that this L1 error cannot be simplified, cannot be amplified.
Maybe it's a technical question, but this L1 and what sense, kind of what is the topology? So is it something, am I missing in topology here? Right? It's not speaking. Because you're measuring somehow, right? You're measuring, but you're measuring the density.
You just need L1 space, L1 in the X and B.
Oh, so just,
The density function is function of S and P, so take L1 more.
Yeah.
okay.
Okay. So now let us discuss why this L1 error cannot be amplified. If it can be amplified. But let's consider the dynamics of going forward. If you are going forward, you see that this error comes from some collision at time tau to 2 tau, and condition on the fact that there's a collision at 0 to tau, the probability that we have another collision is getting smaller because these two collisions are in some sense independent of each other. But if we are trying to go in backward, because if we are trying to go in backward, the particle trajectory just follows the original trajectory, exactly follows the original trajectory. And originally you have one collision. So the second collision happens deterministically with probability 1. So, if we're going forward, this error will not be amplified. But if we are going backward, this error will be amplified to a 1. So, if you're going backward, this doesn't really. So if you're going backward, you will have problem. So, from here, we see that the fine structure of the L1 error determine the error of time. So let us write down the conclusion. Is there any questions?
So because so far we are describing on the board, it's all about. Actually, it makes me feel it's about particle system itself, right?
Yeah.
So the particle system itself, why there's the error of time? So I think
Oh no! You need to compute some probability. For the particle system itself, you definitely do not have error of time. It's just irreversible.
Describing in this black ball is about.
Yeah, you need to think about this. You need to think about the L1 error. In the L1 error, you are trying to compute some probability. You need to show that this error will not be amplified, and this involves some probability.
Also, I want to ask. So I think this is very important in your work. But in general, it's very hard for a PDE problem. If you have short time to go to long time, it's always very hard. But why you emphasize this time the hardness comes from the irreversibility?
In general, if you want to show that to, in general, the difficulty comes from regularity. If you do not have regularity issue, for example, if you look at some equivalence of an ODE problem, you will see that this bootstrap is typically easy. But here, the difficulty doesn't come from any regularity. It just comes from the error of time. Does this answer your question? Okay, thank you. Good. Okay. So as we have explained, the fine structure of the error determines the error of time. So it is worthy to study the fine structure of the error. So in order to do this, we will use the so-called cumulative expansion. We will show the following. Show that the marginal function can be decomposed into the following form, and this form of decomposition is always referred to as cumulative extension. And let me explain why does this expansion characterize the fine structure of the L1 error. Let us separate the case of H is empty or not. If H is empty, it's just a product of one particle functions. And if H is not empty,
What is this ace superscript? What is this ace superscript?
A is, A is just, you can ignore it. It's just a name, F8. It doesn't represent anything.
Well, the FA is like the approximate solution to the Boltzmann equation.
Yeah. If you do not feel good about this, you can replace F8 by N, which is the solution of the Boltzmann equation. Is there any other questions?
Is H S divided by H?
Oh, this H is just some set.
No, you have S.
On the exponent and the F.
Yeah, oh, yeah, thank you so much for asking this. S is the set 1, 2 to S. And H is a subset of this set.
The F remove H.
S remove H. Yeah, this is a. I will give one example so that you can understand this more clearly. But before talking about the example, let me first explain why is the second term characterize the fine structure of the L1 error. This is because the first one is clearly the same as the PI assumption, but the second term, EH is always supposed to be small. It is supposed to be something of order epsilon to V. So those terms can be viewed as some small term. In general, when the size of H is getting larger, EH will getting smaller. So this is some hierarchical thing which characterize error of all orders. Now, let me give you some examples of cumulant that may help you to understand this expansion. Let's imagine that we have 4 different particles. In some time interval, the 2 particles, 1 collides with particle 2, and 3 and 4 does not really interact with other particles. And because 1 collides with 2, we know that there's an interaction between 1 and 2, so their configuration Z1 and Z2 are correlated. But for 3 and 4, since they does not interact with other particles, so we know that the coordinates of 3 and 4 are independent of each other. So in some sense, this term, let's denote, if you compute the probability of collision history of the following form, we see that the probability equals to E12, Z1, Z2, FA, Z3, FA, Z4. So, as you can see, this term will be the EH, the cumulant, and those terms will be the factor, will correspond to the factorized term. And since you know the collision of these 2 particles is a small probability event, and so the fact that 1 collides with 2 is a small probability event. So you can obviously denote this term by OL1 epsilon to V. However, if you only denote it by OL1 epsilon to V, you will see that you lose too much information. That's why we introduce the so-called cumulant expansion. If you denote P as the following form, it will remember much more information. Okay, that's the intuition and the cumulant expansion. So now let me check if there's any questions. Okay, actually we ran almost, I think I'm running a little bit slow, so let me cut all the questions and run a little bit faster. Yeah, if you have some notational questions, please ask me. Yeah, but let us cut all the heuristics, some question about the heuristics.
Excuse me, let me understand. You have not defined the cumulant here. It is the E. Let me ask you a curiosity. Is the first cumulant, is what is called in the literature V function, or is the full cumulant? Because you
No. This is not the full cumulant.
It's not the full cumulant.
Yeah.
So is the V function?
V1?
There is a lot of literature in which this E is called the V function.
Oh, yeah.
What I'm asking is whether this is the V function or not.
This is not a full cumulant, at least for higher order.
So it's V function.
Yeah.
Okay.
So, yeah.
Okay.
Yeah, let's don't care about those details. Okay. Now, in order to we have explained the concept of cumulant expansion, and let us explain the. Now let me introduce a formula for this cumulant, and using this formula, we will be able to prove the PI assumption for a long time. And in order to explain this formula, let me first explain one important concept, which is first introduced in our result, which is called molecule diagram. It's not new in other contexts, but it is new in the study of particle system. Okay. We will always use the letter M, bool symbol M, to denote the molecule. Let me first draw a picture of a possible trajectory. For this trajectory, of course, everything matters. It matters the distance of travel in these pieces, and the directions, and the collision times. They are all important. However, we do not want to remember this information, so we can introduce the notion called topological reduction. Let me don't introduce a rigorous definition. Let me just tell you the intuition. A topological reduction for the trajectory is just is just the procedure ignoring all the distance. And after ignore the distance, we will get a graph theoretical object. And this procedure will be referred to as topological reduction. And this diagram, where we erase all the information of distance, will be referred to as the molecule diagram. And we will also need the following indicator function and events. We will use the indicator function 1m to denote the indicator function of the event that trajectory topologically reduces to the molecule M. Since this is an important concept, so let me accept some questions. Is there any questions about?
So if there are two graphs, two diagrams of where they are different distance, but then in some sense you're saying they're you can how should I say?
Yeah, let me.
They're kind of just one thing.
Yeah, I mean.
In terms of some topology there.
Yeah, I mean, for this diagram and this diagram, we will treat for these two trajectories, they will be reduced to the same diagram. And yeah, I mean, we can even have disconnected trajectories, and those two trajectories will reduce it to a diagram of the falling form. Does this answer your question? Okay.
So the thing is that the model only remembers the collisions and the basic time order of collisions. It doesn't matter the positions, actually Vj and the time, and
These particles are allowed to interact with other particles.
Yeah.
Outside. Yes.
Yeah, yeah. And we can also introduce the so-called layer. We can also introduce the so-called the concept of layer into the molecule. We may consider that as 2 tau, and consider this as tau. And this is 0. For these trajectories, we see that those three collisions happens. Those 3 collisions happens in different time intervals: 0 to tau, tau to 2 tau, and 2 tau to 3 tau. And this diagram will be topologically reduced to the following triangle diagram. For this diagram, we can still retain the information of a layer. Here, although this is a 0, 1, 2. Here, although we do not specify the exact time of the collision, but since this collision belongs to layer 0, belong to the layer between 0 and 1, we will require that the collision time is between 0 to tau. And this diagram will be referred to as layer molecule diagram.
Also,
Yeah.
within one layer, multiple collisions or
Multiple what?
collisions.
Yeah. Within layer, within one layer, we can have a lot of collisions. This is just one special example. Okay. Now, let us state the main theorem of the first lecture. And this theorem will not be proved in today's class. And we will assume this theorem. And in the second part of today's class, we will assume this proposition and using this and sketch the strategy of how to use this proposition to prove the PI assumption. And in the next time, we will prove this proposition. Assume that we have the marginal distribution function of a particle in a canonical ensemble. Then this marginal distribution can be decomposed into the following form. Plus some extremely small error. And besides this, we also have a formula for these coulomps. This is M belong to star, and I will not explain star here. When we use when we use this star, we will state it. Yeah. Currently, let's just forget star. And let me the IM is pretty the expression for M is long, but let me write down some of the mathematical description of this IM. So this is the roughly speaking, what does this IM looks like? And before we move on and take some questions, let me first explain this expressions carefully. There's basically two questions that we can ask. One is P minus R. The other one is what is this interval? Let me first explain this P minus R. Given as we have explained before, given a molecule, we actually also have a notion called label. You know, some particle will belong to this 1 to S, and some particle will be new particles that may. Okay, I will explain the heuristic later, but let me first tell you that in a molecule diagram, there can be some labeled particles. P minus R is the set of unlabeled particles. So this is P minus R, and 1m, this integral over 1m is some function of the initial data. And you are just taking integral over different initial data. Okay, now let me see how many time do I have. I still have 1 minute, but can I get 3 minutes of extra time? Yeah. So let me finish the explanation of the heuristics, and then we will start our first class. Let me explain the heuristics Before we explain the heuristics, let me first explain the physical interpretation of a marginal distribution. The marginal distribution can be interpreted as the probability that as particles, the as particles finally appears at the position Zs at time t. Is there any question?
No. 你从中间往上下推，从中间推。
Oh, okay, yeah, thank you so much. Let me draw a picture for this. Let us consider a molecule of the following form, and this molecule has 3 connected components. And this marginal distribution can be interpreted as the probability that finally at time t equals to, at the final time t, the particle 1 is at z1, particle 2 is at z2, particle 3 is at z3, particle 4 is at z4. So this is the interpretation of ft comma zs, and we can clearly decompose this probability. This is the sum of different molecules of the probability that as particles appears at Zs at t. But on top of this condition, we also have the condition that the trajectory topologically reduces to m. And we denote this probability by fm t comma zs. This fm can be interpreted as a marginal distribution restricted to the trajectory, which is topologically reduces to m. And now, in this example of a molecule, we know that the trajectory in particle 1, 2, the particle 3, and the particle 4 doesn't really intersect with each other. So you can view them as independent of each other. Therefore, we know that for this molecule, Fm T comma Zs can be factorized as the following. This, for the first term, 0 goes to the cumulant. And for the second term and the third term, they will be terms in FA. And because of we have these events of topological reduces to m, we know that Fm equals to n rho over 1m. So this is the intuition of why do we get this decomposition formula. Okay, that's all what I want to present in the first lecture. Sorry, in the second lecture. In the end, let me collect some questions.
Any questions? If N2 and N3 are also collisions, why is it not singular? Why is it not in E?
Collision between which one? I didn't hear you, sorry.
M2 and M3. So
M2 and M3.
so there's also some collision, right?
Oh, yeah, that's a good question. Because we are only computing the probability of these S particles, so we only care about the correlations between the S particles. Although these three collide with some unnamed particles, but these three and 4, 3 and 1 does not have any correlation. So finally they will be factorized. Does this answer your question?
So unlabeled particles are outside this S.
Yeah. We have. Let me explain this. We have n particles in total, but we only care about the first S particle. And in the second and the third molecules, although particle 3 and 4 collide with some other particles, but they do not. 3 and 4 do not have a correlation, so they can be factorized. Does this answer the question? Is there any other questions?
So if there's no question, we will have tea outside, and the next lecture will begin in 22 minutes. Later. Okay, so we start the second part of the lecture. 行，交给你。
Okay, let's continue. Okay, that's the idea of the Kuhlmann extension formula. And before we return to the proof of the PI assumption, let me first analyze some of the examples of the molecule terms. By molecule terms, I will always refer to this term. So let us look at some examples of IM and analyze a possible upper bound. Let us first consider the following diagram. This diagram can be interpreted as events at one label particle, S equals 1. One label particle collides with one other particles. And in the last sem, we have explained that the probability that two particles collide with each other. In the last sem, we have when we derived the Boltzmann-Graf scaling law, we have explained that within time t approximate of order 1, the probability that two given particles collide with each other is of order epsilon to d minus 1. However, for this unnamed particle, we have n different choices. For this part, let's denote this by star. Star can be any number, 2, 3, all the way to capital N. This capital N is a random number, but its excitation is known. So we know that roughly speaking, the probability is equal to n times epsilon to d minus 1, which is approximately equal to 1 according to the Boltzmann-Graf scaling law. This is one example of diagram. Since this is a 1, this will be interpreted as one of the main terms. We can also consider the other diagram, 1, 2. This diagram is topologically the same as the previous one. However, both of the two particles are labeled. And according to this heuristic, and according to the above heuristic, we know that the probability of this event, let's denote this by M1, this by M2. So we know that PM1 is of order 1, PM2 is of order epsilon to d minus 1. This is another example. We can also analyze the following example, the third example. These correspond to the events where you have one label particle in S, and this particle collides with another particle for once, and then they collide again at a future time. This doesn't happen in a Euclidean space, but this will happen in a torus space. So let us consider this example. In this case, the size of this is IM. I am trying to analyze the sum of the size of these IM terms. It's not PM. IM is the probability that the trajectories collides in this way, and for this diagram, we can again analyze IM. For the first collision, we get a probability n times epsilon to d minus 1, since the n comes from the trough at here, the trough of the particle labeling at here. Epsilon to d minus 1 comes from the collision at here. And for the second collision, we again have 1 epsilon to d minus 1, but here we don't have n because at the second collision, it's all the label has been fixed. So in this case, IM will of order n times epsilon to d minus 1, to d minus 1. So this is this diagram. And this is of order epsilon to d minus 1.
I have a simple question. So so currently you're doing the calculation of these things very heuristically.
Yeah.
But if you were were to rigorously prove this, is it simple to prove these type of
It's
or is it-
yeah, it's extremely simple. It's just two particles. You take the initial velocity and compute the probability. Yeah, it's not easy, but it's computable. You can compute it. Yeah. In our paper, we really compute the probability. Okay. This is okay. This corresponds to the forward two collision example that we have explained in the irreversibility part of the lecture. We can also consider one molecule. We didn't define this molecule, but I think this should be intuitive to you. Actually, this molecule is not well defined. Let us consider the following molecule where the particle going forward and then you reverse the time arrow, so the particle will return. We will follow the original trajectory and return to the initial value. In this case, you get n times epsilon to d minus 1 for the first collision, and for the second collision, as it happens deterministically, so you don't get another smallness. So this is of order of 1. As you can see, if you're always going forward, the second collision is a small probability event. But if you're going backwards, you get a 1, which will alternate your one term. And this is why you will finally return to the initial term.
So sorry, I think. So when you write the half circle, this curved line, do you mean you ignore what's going on in this evolution? Or do they finally reproduce?
I mean, in a Euclidean space, this never happens because two particles can only follow the straight line, so this never happens. But as I said before, we can consider. I come up with this example because this example is simple. If you consider torus, it is possible that you have a collision, and after in the torus it is possible.
But then this location means there's no actual collision with this particular two particles in this.
You only have this molecule. Just means that you only have these two collisions. You do not have a collision at another collision at here.
So then why it's different if you go forward? So when you say go in the backward, you mean you look at the graph from up to down?
Going backward doesn't really make sense in the molecule diagram. So you just. I just trying to see that if you're going forward and backward, the probability is n to n times.
Sorry, could you repeat this again? How to get this difference? So I understand this epsilon d minus 1. How do you get n multiplied epsilon d minus 1?
Because this is labeled as particle 1. This is unlabeled. For the first collision, you get n times epsilon d minus 1. For the second collision, you get nothing. So the probability. This is very complicated questions. So if you're still stuck at here, we can discuss after the class.
Thank you.
You can keep this because this is irrelevant to what we want to discuss later. Okay. Now we have introduced the equivalent extension formula. As we said before, in order to show Boltzmann, we need to show that Ft is in order to prove Boltzmann, we need to show that Ft is approximately a tensor power we need to show that it is approximately a tensor power. And from this Coulomb expansion formula, we know that Ft is equal to a tensor power plus some higher order term. So in order to justify this is pi. In order to justify pi, it suffices to show that all other terms like this are small. So, but Fa terms are not small. They are just min term. They will be close to the solution of the Boltzmann equation. So, what we need to show is that this EH will be small. According to the Coulomb formula that we have written down here, EH, actually the integral of EH.
Sorry. Here the solution H is not right. H is not.
Thank you so much. EH, there are one norm of EH is sum over the integral associated with some molecules. When did we start?
40 minutes ago.
Okay. So we have the following extension, and in order to show that EH is small, it suffices to control two quantities. The first one is we need to show that there isn't too much term in the sum. This is the first term, and this is first thing that we need to show, and the second thing that we need to show is that we need to show that each IM is small. If we show that too many terms, if we show that there isn't too many terms and each term is small, then we will finish the proof. And the strategy goes like this. In order to upper bound the IM, we need the following notion, which is called cutting. I don't want to present the full detail of the cutting operation, but I think because it's intuitive, so let me just draw a picture. Okay, this is one molecule diagram. We can apply a cutting operation. In that way, we just choose a line and try to actually choose a line, not a reverse definition, and it's pretty restricted. But let me just explain this intuitively. We just choose a line and cut all of those edges into two. So let me copy another such diagram. Okay, this is just another such diagram. The cutting means that we just cut all these three edges, and we choose one of them to cut as three. Sorry, cut as six. And we choose the other one to be cut as 3. And for those cut as 3, we replace the generated edges by the so-called fixed edges. And for the other one, we replace the new edges by free edges. And we probably will do not have time to explain the full detail of this in this class. But currently, let me explain the intuition of the fixed edges, because this is a new object. You can view M as some integral over 1m, integral over some integral. The fixed edge means that the variable is fixed. We will explain the precise meaning of this. Of the fixed end in the next time. In this time, let's just understand everything intuitively.
So you can do this cut. Essentially, you're doing some relabeling.
No, it's not relabeling. It's something like it's okay. It's good for me to explain some of the intuition. We know that let me explain the intuition a little bit. M is union of the union of M1 and M2, right? So what is IM1? IM1 tells us that there are 1, 2, 3, 4, 5. There are 5 collisions. And IM1 tells us that there are 1, 2, 3. There are 3 collisions. And IM2 tells us that there are 2 collisions. So actually we know that IM1, so IM will equal to IM1 times IM2. As the product of IM1 and IM2 is the intersection of these 2 events. So you have these 3 collisions and these 2 collisions. So you have all these 5 collisions. So your question is for the integral, can we just simply can we just factorize this integral? That's impossible because this is pretty similar to the following integral. you take this to be the function f, and take this to be the function g, and this integral is pretty similar to f z1, z2, g, z2, z3, and you have integral over dz1, dz2, dz3. If you do not have the common variables, yes, you can factorize the integral. It's very easy. However, you have this common integral. So, but you can still apply the Fubini. You can still apply the Fubini theorem. You can still apply the Fubini theorem to conclude that this integral equals f z1, z2, integral of g z2, z3, d z3, d z1, z2, and you can take supremum over this integral. So you have supremum z2 integral of g z2, z3, d z3, integral of z1, z2, d z1, z2. So yeah, so now you see that g this is M2, this is M1. You take g. Now you see that g is IM2, and z2 is a common variable.
It should be less than or equal to. Less than.
You see that z2 is a common variable, and common variables corresponding to the variables of these three edges. Yeah, we will present the details, but now let's take everything intuitively. So as you can see, if you apply integrals of the following form, you see that this integral of g, the common variable is a fixed variable, and in the second integral, the common variable is an integral variable. So you see that here you get three free edges, and here in the above you get three fixed edges. Fixed edges means that in the integral you get in the integral you do not have integral, instead you have a supremum. So in this computation, if we take f to be 1 and 1, g equals to 1 and 2, then we will see that Im equals to integral of 1m, which is less than these two functions. This is the first function is Im2. The second function is Im1. This is one of the most important conclusions in our second lecture.
So the cutting is to destroy the loops.
And we refer this as cutting lemma. This lemma tells us that if you cut one large molecule into two smaller molecules, then the integral of the large molecule is less than the product of two smaller molecules.
Should I understand conditional expectation?
Yes, you can also view it in this way. Is there any other questions?
But are these fixed edges specifically chosen?
No,
The
you take
data
supreme.
setting.
It's not specifically chosen. It's in some sense you take the supremum, and I said that it's fixed only because it's not appears in the interval.
When you take superhuman, there could be 2 points colliding, coinciding. Is there any similarity?
Yeah, that is. This supremum can be infinite. Yeah, it is possible that it's even infinite. I mean, but that's something we want to avoid.
Some kind of sub-additivity.
Yeah, some kind of adjective, sub-adjective.
So can I understand it like this? So you have the output of M1, and that will be the input of M2. And then you kind of change the M2 input to be the kind of the worst case.
Yeah.
But how would you design those new inputs of M2 as the you call it fixed edges? But what are those fixed edges? How would you choose those inputs?
We will explain. This is not very intuitive thing in this picture. In the next time, I'm not sure if I have time even in the next time, but I will see that this Dirac function representation of M, and where this cutting lemma is actually maybe we can discuss this after the class.
One more question. So, strictly speaking, I don't feel M equals to M1 is union with M2, right? Because when you're talking about this graph, you have a cross or not, it's different graph, right?
How do I say this? Yeah, I mean, this is just a justification. If you do not believe it, then you just keep your thoughts, and we will because there's a lot of questions, so in the next time I will present the proof I will explain how do we convert this to a Dirac function representation, and we will explain why in the Dirac function representation this cutting lemma is true.
Actually, my question is just one notations, because when you say M, you mean a graph.
Yeah.
But when you see M1 and M2, you have added some extra labels, which is 3 cross.
Yeah.
So from this perspective, why is M the union of M1 and M2? It just seems like, because
The
It would be
node
the
of
node set
the
of
node
M2.
set is
Set of M1 unit node set of M2.
the node set of M1 is the union of M1.
Like when you talk about graph M, sometimes you talk about graph M, sometimes you use the same method M to denote the node set, right?
But when you talk about node set, you don't care about the star. You don't care about the cross.
The cross just indicates the fixed M, but this is in terms of the the set, just a set.
Yeah, let me see one thing. Cross doesn't really you can in some sense ignore the cross. It would except but if you compute IM, you must consider the cross, because when some variable is labeled as cross, then it does not appear in the interval. We actually didn't define IM for some M with cross. This is an extension of the definition. For molecules with crosses, IM will define to be the integral, but of the variables without the cross. Is there any other questions? Okay. Given this cutting lemma, we will see that. Given this cutting lemma, we will see that if we are able to decompose to cut M into smaller and smaller pieces, like M1, M2 to Mk, then we know that the integral IM will be less than the product of IM1 times dots times IMK. And if we are always able to decompose a graph into some small elementary graph, then it suffices to upper bound the integral for some specific elementary molecule. So this is how
Excuse me, but here we forget about the whole business of labeling anymore.
no, it still appears.
But when you do like this cutting, like how do you?
I mean, how do I say this? Currently, let's forget the label. This is some technical point, so I don't want to explain this in this course.
Can I ask a question? So let's say you take the union of M1 and M2, so then you form a larger group. Then the larger group preserve those collision information. So,
What do you mean?
So
The collisions are represented by nodes, or we call atoms.
Right.
Yeah, so the union, preserves all the collisions.
So as
in
long
it.
as it knows what is it and the edge. If you take the union of M1 and M2, then you put the edge together.
When you do the cut, one edge is cut into two kind of 1, 3, 1 fixed end, right? And then of course you can formally kind of put them together to recover the edge, but we only do the cutting, so it's.
So you don't do the opposite direction.
We don't.
We can never do the opposite direction because it's inequality. You cannot. We do not do something like cut recombination. Yeah, those doesn't work because this is an inequality. Okay, so since we have now our task, we have two tasks. One is to analyze that. One is to analyze the number of terms in a summation. The other one is to show that the IM is small. So the second task of showing IM is small now is decomposed reduces to design a specific cutting algorithm that can decompose IM into some elementary molecules. And before we discuss the cutting algorithm, let me first explain some examples of the elementary molecules. The first elementary molecule is a molecule of degree 4. Let me first reserve the word degree. We will call this degree 4 node. Let me explain the word degree. Degree in the graph theory is just the number of edges connected to one node. But in our setting, a degree is the number of free edges connected to one atom. So this one is not a free edge. So this is degree 4, this is degree 3, this is degree 2. This is called 3-3 molecule because it is graph of 2 degree 3 molecules. And we can analyze the size of these integrals. I will not present the analysis because it's very complicated. For degree 4 nodes, I just tell you the conclusion because the conclusion is easy to remember. For degree 4 node, IM is bounded by epsilon to d minus 1, which is a lossy vector. This is a large factor. The integral of the degree 3 node can be bounded by 1, and the integral of degree 2 node can also be bounded by 1. And the integral of the 3-3 node, 3-3 components can be bounded by epsilon, and of these two can be bounded by epsilon to some power. Let me explain a little bit about these numbers. Actually, when you see fixed edges, it basically takes the same rule as a label particle. For these, the collision probability is always epsilon to d minus 1. So this one is one label particles, so you have n. So n, you have n product with it, so it's order 1. And for degree 4 node, you have 2n. So you have 2n, so due to Boltzmann-Glass scaling law, it's epsilon to negative d minus 1. For two, you have two. For degree 2 nodes, you cannot think about this as two label particle. I don't know how to explain this, but the result is 1. So yeah. For 3-3 node, it's basically that you have two particles, two label particles with an unlabeled particles. So the collision probability is n times epsilon to d minus 1, epsilon to 2d plus 1, so it's less than epsilon to d minus 1 in some sense. Actually, we cannot get such good estimate. We only get some small power of. Is there any questions?
Yes, because IM2, so the meaning of 4 and IM2 seems to be different. When you have this M, so what do you mean? The first graph means two arbitrary particles colliding with each other, right?
Yes.
So this you get X. So then the second graph means one particle.
This one is definitely different from a label.
So one given particle. So it's not one given particle.
Yeah, it's not one. How do I say this? I mean, these can only be understood formally. I just come up with this just to help you to understand the.
So let's understand this way. So in the formula of IM, we have this epsilon to the negative power in front and positive negative. I mean.
Yeah, this.
Positive,
this is
epsilon power in front. So basically, you think that each of these is the actual integral paired with some particular power of epsilon, and after pairing with epsilon, you get this.
Yeah, but you cannot explain it this way because the formula that I read here doesn't count anything about fixed. So yeah, things can only be understood. I mean, only when I really do some computation, I can explain this.
Excuse me. So I'm not sure my understanding is right. So let's say, each collision there will be a factor epsilon to d minus 1, right? So then the factor of n is just the counting number, right? How many possibilities?
Yeah, I mean, this n, what the n that I wrote here is not really n. It corresponds to some factor here. So let's separate the result into two parts. Epsilon corresponds to the integral over Im. So whatever it's fixed or not, it's collision between two particles. It's always epsilon to d minus 1. But for the for the number for the different distribution of fixed ends, the combinatorial numbers are different. So we get these here. Yeah, but this cannot be. So at this stage, you cannot understand this. So I suggest you do not ask so much questions. Yes, because I cannot explain this at this stage. Yeah, I just want to help come up with a rule to help you to understand, to remember the result. Okay, good. So if you can remember the bond for the integrals for the elementary molecules, now we can discuss the central strategy of our proof, which is the design of a cutting algorithm. As we have seen, in order to upper bound this integral of M, it suffices to define a cutting algorithm that decompose M into many elementary molecules. But as we can see, elementary molecules are different from each other. We definitely want 3 as many as possible, because for this we will get a small factor, we have a gain. For those one, it kind of appears, but we don't like it. For this one, it's extremely disgusting. We never want to see it, but as you can see, we sometimes cannot avoid it, but we need to control the number of degree 4 components.
Sorry, here by elementary you mean there's no cycle?
No, it's elementary just means that it's the simplest diagram.
Elementary means one of these 5.
Yeah, means one. Yeah, maybe there are several other examples, but it's a list. It's a list of several chosen molecules. Yeah, in my lecture it means this part. Okay, let me write down the requirement for the cutting algorithm. Okay, let's discuss the so-called cutting algorithm. For a cutting algorithm, we want to decompose M into M1 we need which satisfies the following requirement. The first one is number of nodes in Mj is less than 2, and no non-elementary thing can appear. No, this one, etc.
I have a question. So at first there's these 5 elementary molecules. The last 2 are small. So, and then border 1 ones are, if you were to compute this IM and you found that some of the terms are border 1, you don't want, somehow you don't really want to estimate. You need to keep them, right? In your, how does it, okay, suppose you know that this is an order 1 object. Then you don't, that's not an error, right? It's an order 1 object.
Yeah, but for IM, we not only want it to be bounded, we also want it to be small. Because as you can see, there will be actually many terms in the summation, but then we can only show that it's not too many, but there's still many of
So
them.
you're saying there's not too many order 1 terms in the summation?
All the one.
There's no
but
order
the
one
thing is that the thing is that you need to find sufficiently many good things.
Yeah.
In 3-3.
Yeah.
You don't worry about how many normal things. You only need to control the bad things.
Yeah.
Okay?
I mean, you want good thing to be as many as possible, because only when good thing you have a lot of good things, you will have these. You will have smaller things. Those one are 3 and 2 components are always something that you can
Because
use.
then you have number 4, and then number 1 over there, and then number, say, 4 over there. And when you decompose the graph, you get those 2, and then you estimate them. So how does that work? And then the product, then they're order 1, right?
Yeah,
So
yeah, we will do this. Yeah, we will do this. This is how do you design an algorithm. You need to design an algorithm. There are different ways of cutting. You need. Let me show you one example. Let me show you one example. For this case, you can first erase this one. You get a 3-3. This will be a good thing. But if you continue to cut this, you cut this 3-3 into 2-3. Then you get 2 normal things, and you get a 1 term. But if you don't cut it, you get you know that this term is actually a small error. So you need to choose an algorithm. You choose when to stop, when to where to cut, to make the bond as small as possible. This is inequality. For different cutting strategy, you can get some strategy is large, the bond is loose. For some strategy, the bond is tight. Okay, this is first requirement. We do not want those bad things happen. And and for the second requirement, we want in the algorithm as few degree 4 nodes as possible. We want to design the order of cutting so that in the final result, the number of degree 4 nodes is as few as possible. And in the final result, we also want the 3-3 components to be as many as possible. This is a requirement of the cutting algorithm, but the bad thing in this description is that we didn't specify what do we mean by. We didn't specify quantitatively what do we mean by as few as many. So that is something that we want to explain right now. I don't want to erase it, but I make a cross here to indicate that you should skip this part of the part. Okay. Now, let's return to our main task 1, task 2. We need to estimate 2 things. We need to estimate the number of terms in the summation, and we need to upper bound the size of each term. So So we need to estimate the sum, and we need to estimate number of terms. Let us first discuss the upper bound of the number of terms. This is where we start to use the condition star. This is where we first use a condition star. The condition star says that the diagram can be decomposed into a few different layers, and this is actually the first requirement of star. The star tells you that within each layer, the molecule M is a tree, is almost a tree. And this is a standard combinatorial argument tells us that there are only exponential many choices of non-isomorphic traits. So we know that this is a tree, and a tree implies that there are the number of choices is bounded by 4 to NL, and let's denote NL to be number of nodes in ML. This is one source of combinatorial factors. There's another source of combinatorial factors. Imagine that you have a collision. Let's imagine that this is ML. And imagine that you also have another layer. Let's imagine that this is ML minus 1. Let us look at the interface between. These two layers of diagrams. In the interface, we need to decide which particle goes to which particle. And let us denote the number SL equals to the crossing particle line from L to L minus 1. And then we know that there's a combinatorial factor which comes from choosing which particle goes to this particle. There is a permutation. This is proportional to a permutation. So let me write this more carefully. Within layer, within layer, we get within a layer, we get a tree. We get a combinatorial factor 4 to the NL, and crossing layer. We get a permutation, and the permutation is given by the factorial SL, and therefore the total number of terms can be bounded by pi L 4 to the NL times SL factorial. We keep this factorial because factorial is typically much larger than the exponential. What's your question? Oh, I already ran out of time, so yeah, we can discuss this after the class. Sorry about that. Let me finish this as quickly as possible. Okay. Now this is a combinatorial factor of the number of terms, and there's another requirement in star which says that NL is bounded by which says that NL and SL is bounded by some logarithm, some power of logarithm. This is another requirement in star. So using this, we can bound SL factorial by SL to SL. And therefore, this can be finally bounded by pi of L 4 to the NL times logarithm of epsilon C SL. This is the number of terms. And for the size of each terms, it can be, if we have an algorithm which decompose a diagram into some elementary molecules, then we see that the IM is bounded by epsilon to number of 3 components. It is the number of those 2 components. And let me erase our view. And this is a gain factor. And we also have a lossy factor, which is epsilon to negative d minus 1 to the number of 4 molecules. And we also have another gain factor, which is tau to NL. Let me explain why we have this tau to the NL. This is because for each collision, we know that it happens within some layer L, L minus 1 and L. We know that the collision happens within a layer L minus 1 to L. So these will have. So we have a requirement. If we denote the node by n star, there's a requirement that the collision time must belong to L minus 1 tau times L tau. Therefore, we know that the measure must be bounded by tau since there are NL nodes. So we will get a tau to the NL. So now we see that the sum of IM can be bounded sum of m I m can be bounded by the absolute value of the sum and the magnitude of each IM. We can always ignore the not 4 to the NL because it always be bounded by tau to the NL if we take tau to be less than 1/4. In order to make the rest, and for all other terms, we have the number of we have a gain factor, which is called the number of 3, and we have lossy factors. We have lossy factors, constant times the number of 4 molecules, and constant times logarithm of sum of L as L. So the family is if we can construct an algorithm where the number of 3 molecules is much greater than not much greater. I mean up to a constant like greater than 100 times number of 4 molecules, and the 3 is also number of 3 molecules is also greater than 100 sum of maybe not 100 greater than some small ratio of sum of L as L. If we can construct one cutting algorithm where we get enough 3, I mean as many 3, so now this is a quantitative requirement of a number of 3 must greater than a small ratio of the crossing number. This is the quantitative requirement of the third term, and for the second term, we need the number of 4 molecules to be much less than 1/100 by the number of 3. And so this is the requirement of the algorithm. And in Yudom's lecture, he will explain how do we really construct one algorithm which satisfies the requirement of 2 and 3. And in the next time, I will explain some of the missing detail in the derivation of covalent formula. Okay, I run a little bit fast at the end, so let me now accept questions about the final part. Is there any questions? If for somewhere I didn't explain it carefully, you can ask me to talk about it. Okay. Is there any question?
Sorry, maybe naive question. Why it is less than log epsilon in the
Here's a requirement in star which tells you that the number of nodes and the number of crossing numbers is less than some power of log.
So that sum is not over all different types of molecules.
Yeah, it's just sum over a subset of all molecules, and the subset is prescribed by star.
But you didn't tell us exactly what star is.
Yeah, and now I tell you some of the requirements. In star, you need to have you need the within each layer the molecule must be a tree, and the number of nodes and crossing numbers must be bounded.
And it's not obvious how time, the time actually plays into this entire thing. One thing I don't understand is how the time is played into this component, right? And second of all, I don't understand is how you root out all this like infinite type of collision.
Yeah,
How
this
can
is
you
the-
find that
So
time?
first of all, the
There's a
time.
truncation argument that we would.
So first of all, the time comes into the number of layers. So the number of layers is huge, but very tiny compared to epsilon. Okay, this first thing. Second thing is that the case of infinite collisions is excluded by a truncation, and this truncation tells us basically if you have more than 1,000 recollisions, then you take the time where you have exactly 1,000 recollisions, and that already gives you a small kind of probability, and you don't need to consider the 1,001 event and beyond. Okay?
Is the zero molecule bound to appear, or you don't want it to appear in the algorithm? Is the zero molecule, for example?
Oh yeah. For you mean this one?
Yeah.
No, for this type of molecules, even one of them it cannot be appears.
Okay. No. They would not appear, or you don't want it to.
I don't want it to appear. Let me come up with a stupid cutting where it do appears. Okay. Yeah. Let me give you a stupid example. Let us consider the following molecule. You first cut this one. You got a cross at here. Then you cut this one. You got a cross at here. Then definitely there's if you just deliberately want to construct make this appears, it will appears. Yeah, but you need to carefully choose the algorithm so that none of such pattern really appears.
So, I don't know if I understand correctly. So, are you trying to prove any molecule such that two labeled particles are connected should be small? Is this the goal? If two labeled particles are connected in your molecule, then this molecule should be small. Is this the goal?
No, the goal is that you count. I mean, the goal are written here. I mean,
Yeah, let's say the goal is to prove that any molecule satisfying the requirement star is small, and then the what you say is part of star.
Yeah. Part of I didn't tell you a lot. There's actually a huge number of requirements in star. What you are saying is that in for a molecule, the molecule in the molecule where one is connected to, two is connected to three. This is one requirement of the star.
So what about graphs not satisfying star?
Then it will not appear in the Kuhn expansion. You know, in the Kuhn expansion, as we explained in the intuition, like h equals 1 to 3. If h equals 1 to 3, then 1 to 3 must be there must be correlations in 1 to 3 in order for this term appears in the expansion of h. Yeah, so this is part of the requirement in star. This will be carefully discussed when we present this cutting algorithm. Yeah. Now I just want to give a brief overview.
So let's still ask. So I think it's exactly this picture. So you were trying to explain if you want to go backward, it's different. Could you do this again?
Which time?
So this picture. No, the picture on the screen.
Oh, okay.
So you were explaining that.
Yeah, we discuss it after the class.
Okay, so I think this is the end of the day. So let's set the speaker.